Welcome to the next in the series on organic chemistry podcasts, or what I like to call Dr. Brian Lloyd's scribblecasts. In today's podcast, we are continuing with topics in bonding. The last podcast, we took a look at some of the types of chemical bonding, and then we learned how to do or construct Lewis structures and determine formal charge. Now that we can draw molecules, we need to come to an understanding of some basic concepts in bonding. So we're going to be defining terms like bond distance and atomic covalent radius, such as you see in front of you, as well as take a look at electronegativity, bond dissociation energies, dipole moments, and then finally close with a quick look at different types of chemical formulas. Now, when we look at a Lewis structure, we are provided with the atoms linked to each other through bonds, and we show all the lone pairs. It is important to recognize terms such as bond length, or which is sometimes called bond distance, or atomic or covalent radius, for these concepts can be important in the construction of molecules. Bond distance is defined as shown, the distance between two nuclei of atoms joined by a chemical bond. That is, if we draw, for example, two hydrogens, a Lewis structure for two hydrogens, which are bonded together. The bond length is the actual distance between the nuclei of those atoms. There are a variety of ways of determining such distances. For large atoms in molecules, one can carry out X-ray diffraction on crystals and determine the exact atomic coordinate position. There is some variation due to thermal motion, however. If we want to find the hydrogens, you can also carry out neutron diffraction techniques. Both techniques allow you to actually measure distances in nanometers or angstroms, whichever units you wish. Measuring the actual radius of an atom is much more difficult. You see, an atom consists of a nucleus and then electrons in orbitals, and you might have s orbitals, you might have overlaid with p orbitals, and so you've got your p's, etc. And so the question becomes, how far do you measure out? Remember, the edge of the orbitals, these orbitals are just the square of the wave function, the probability distributions, and depending on whether you choose 95, 96 probability, these sizes may vary slightly. So how far do you measure out from a nucleus to get its radius? Remember, radius is this far. Well, we defined it as half the bond distance between the nuclei of two identical atoms. If you use two identical atoms, such as we did in our previous example, two hydrogens bound together, we can assume that bonding, right, and of course I'm not drawing these correctly, so I'll just make it a bit bigger. Excuse my poor drawing. Okay, that halfway along this bond, the two edges of the orbitals come into contact. Now, we talk about orbital overlap in bonding, but what we will do is use half the bond length to represent the atomic radius. And this works well. Now, if we do this calculation and actually measure atomic radius, we get some interesting results when we look at the periodic table. So if you've got a periodic table in front of you, or pause this presentation and go get one, and you take a look at the periodic table, as you go across a row, which is sometimes referred to as a period, such as row 2, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, it turns out that the atomic radius decreases. And I'm not going to worry about why. I mean, we could get into it You will be covering this in your general chemistry course. Suffice to say that the electron-electron repulsion when you're filling the same subshell is not as great as the increase in attraction due to adding protons. And so the atoms shrink. And so lithium is much larger than beryllium, which is larger than boron, and fluorine. All right. So as you go to the right, the atomic radius decreases. What about down a group? What if we compare fluorine, chlorine, bromine, iodine? What happens? Well, what happens now as you go down a group is that, yes, you're adding more protons in the case of chlorine and as you go to bromine. But you're also putting electrons in outer shells. I mean, the fluorine has its electrons in the second shell. The chlorine has its electrons in the third shell. And it turns out, as you add another shell, the electron-electron repulsion predominates over the increase in number of protons. And so the outer edge or radius of the atom increases. So as you go down a group, it increases. So the smallest atomic radius is to the right top of the periodic table. So to the right of a period, and we call columns groups to the top of the group. So essentially fluorine represents one of the smallest atomic radii, other than hydrogen, of course, which is very small because it can fall right above fluorine. And we'll leave that discussion to other times. So suffice to say, smallest atomic radius, the upper right of the periodic table. All right, let's continue this discussion now by taking a look, just quickly, at a type of bond. If we were to draw a Lewis structure for the molecule HF, fluorine has 7 electrons, hydrogen has 1. And I'm going to do this really quickly because I don't want to spend a lot of time. Total number of valence electrons, 8. And what essentially is the hydrogen bonds to the 1 electron of the fluorine. And that leaves 3 lone pairs around fluorine. Okay. And then we could calculate formal charge of the fluorine, and if we do, we find out it's 0. What's interesting is if we do a formal charge calculation, we assume that the electrons in the bond are shared equally. But in actual fact, if we're changing the number of protons, and electron-electron repulsion is playing a role on how closely electrons are held, different atoms have a different strength of attraction for the electrons. As a result, in reality, electrons are not shared equally. And so there is a factor we wish to look at, which is referred to as electronegativity. Now, electronegativity is going to be important in many aspects. And we're going to be using it a lot. So I'm going to give you a trend you need to memorize, electronegativity, and a definition. It gets sloppy at the end. Electronegativity. What is electronegativity? It's a measure of the electron attracting power of an atom. Okay, so it's a measure of the electron attracting. Of course, I won't be able to fit this. Ran out of space. Electron attracting power of the atom. Okay. Now, it turns out, if we look at this in terms of the periodic table, electronegativity parallels small, increasing electronegativity parallels small size. That is, electronegativity increases to the upper right of the periodic table. And so we can get a trend. Fluorine is more electronegative than oxygen. Oxygen is more electronegative than nitrogen. Also, down a group, fluorine's more electronegative than chlorine. Chlorine's more electronegative than bromine. oxygen is more electronegative than sulfur. It is important and useful sometimes to know who's more electronegative, oxygen or chlorine, when there's no obvious relationship in period or group in a periodic table. And that is why you're going to be given the following trend to memorize. Fluorine is more electronegative, greater than, oxygen, who's more electronegative than nitrogen, who is the same as chlorine. These guys are close together. Who's more electronegative than bromine, who's more electronegative than sulfur, carbon, and iodine, who are similar. These guys are all similar. And these are more electronegative than hydrogen and phosphorus. And those two are more electronegative than the metals. Metals such as aluminum or boron, etc. Okay. Aluminum's definitely a metal. Boron's probably on the transition to the metals. All right. Electronegativities are very important in determining a concept we're going to discuss shortly called bond polarity. And you must remember that electronegativity is a measure of your power to attract electrons. So if you are more able to attract electrons, you are more stable when you bear a negative charge. So electronegativity is an important concept we're going to be applying later on as we go on. All right then. What we want to do now is begin looking at a concept we mentioned earlier in a previous lecture, and that is the concept of bond energy. I mentioned last lecture that when you form bonds, atoms are attempting to get to lower energy. Thus, bond formation corresponds with an energy release. Because of this, we can measure energy in terms of enthalpy, or delta H. Because bond formation releases energy, delta H, that is negative, is often corresponds with bond formation. Delta H positive is what is required to break a bond, okay, or bond breaking. Now, if we take a look at our simple diatomic molecule, hydrogen, H2 gas, two hydrogens bonded together, we can measure the bond dissociation energy for this. We can actually do a reaction which cleaves this bond and measure the heat energy given off. And it turns out that the bond dissociation energy, or BDE, is measured as 104 kilocals per mole. Okay, kilocals per mole. Now, when we cleave this, what we end up with is the free hydrogen atom, which consists of a proton and an electron. So we get two of these. Okay. When you have an unpaired electron, you are referred to as a radical or a free radical. We'll be using this term in the course as well. Now, you might notice when we broke this bond, we broke it in half. That is, one electron of the bond went with one hydrogen, one electron went with the other. This is called homolytic cleavage. Homolytic cleavage. So we've carried out homolytic cleavage of the bond. Now, what alternative cleavage could we conduct on this molecule? Well, if we wished, we could have broken the bond so both electrons went with one atom. If both electrons went with this H, then you'd have two electrons here. Hydrogen has one electron and is neutral. Add an extra electron and you've got a negative charge. The other hydrogen would have lost its electron, so it would just consist of a proton, which is positively charged. It would have generated ions. And this is referred to as heterolytic. Heterolytic cleavage. Okay. Now here's a question for you. When we're measuring bond dissociation energy and get 104 kilocalories per mole, we're actually conducting homolytic cleavage. Why, when determining bond dissociation energy, would you want to carry out the experiment so that you're doing homolytic cleavage? The answer is you want to measure the total force of attraction, okay? You want to put in the total energy necessary to break that bond. The problem with this system is these two will still be associated by a force of attraction, and that will give you some energy back because plus attracts minus. In these neutral systems, there's less attraction. There's still some small amount, but there's less. And when you break the bond, you'll get 104 kilocalories. In this system, if you actually did the bond breakage, you'd probably get a smaller number because there's still some ionic force of attraction in this system. So homolytic cleavage will give you a more accurate measure of bond dissociation energy. Again, free radical is any species with one or more unpaired electrons. So if the electrons are paired, this is not a free radical. You must have a single unpaired electron to be a free radical. All right. Well, what can we do with bond dissociation energy? We can actually generate or calculate heats of reaction. How do we do this? Well, suppose I give you a simple reaction, such as, say, hydrogen reacts with Br2 to produce 2HBr. And I tell you to calculate the delta H for the whole reaction. That is the heat of reaction, or heat of formation for HBr from hydrogen and bromine. When we calculate this, we would have to go to a table which gives us the actual enthalpies of reaction for these bond breakages. And when I'm going to solve this problem for delta H for this reaction, I've got to take the approach where I ask myself what's happening to each reagent before I can make the HBr. Or, what does the H2 have to do before it can react with the Br2 to make HBr? Well, clearly, since we have only one H attached to one bromine, I must break up the H2. And so I start writing down these half reactions, these reactions which must occur before we can produce HBr. Now, when I say must occur, they must occur on paper because they will allow me to calculate the actual heats or enthalpies. But it is not necessary that this is the actual mechanism by which this reaction proceeds. So don't think we're showing you the way the reaction really takes place. It's more we're doing a consideration of what must happen to the H so that we can get at the delta H values. So this will work from splitting up H2. I now have an H dot, H radical, that I can react with a bromine to build HBr. Okay. Well, what must Br2 do? Well, Br2 obviously must do the same thing. It must split into two Br dots. Well, now how do I build an HBr? Well, I could envisage an H dot reacting with a Br dot. And that will give me my HBr. And because I've got two HBRs, this must happen, right, twice. Okay, so I can write delta H, and I can get these from a table. Now the table I have gives the delta H values in kilocalories per mole or kilojoules per mole. And it really doesn't matter which one you use, as long as you're consistent and use the same units throughout. But the question on a test you will be given will usually specify the units for the calculation. If not, it really doesn't matter. Now I'm going to use kilocalories, and I'm going to use a table and look up some values. Notice that this is the breaking of an HH bond. So I can look up the H2 bond dissociation energy. Okay, now if I look that up, it's 104.2 kilocalories per mole. So I'm going to put this in kilocalories. Oops, kilocalories per mole. Okay, so the delta H value I get is 104.2. Is it going to be positive or negative? Well, let's think about this. We said atoms go to low energy when they form bonds. They release energy. Bond formation is negative. Are we forming or breaking the bond? We're breaking it, so it must be positive. So we've got plus 104.2 kilocalories per mole. What about Br2? If I look up Br2, I see a 46.3 on this table. These numbers may vary depending on what table you actually use. Are we making or breaking the bond? We're breaking the bond, so it's positive. HBr, if I look up HBr, bond dissociation energy is 87.4. H dot plus Br dot forms a bond. It's negative. 87.4 kilocalories per mole. And in fact, I'm going to write that over here. Because, as you can tell, it is times 2, because we're doing this twice, right? So 2 times that. What do I get? I get an 8, 14, 16, 17, negative 174. Running out of room. Okay, so let's put this over a bit. So what did I have? Negative 174.8. So if I add this up, okay, I add these numbers up, what do I get? Well, this is 146, that's 150.5, right? 150.5, so that's a 3, 150.5, that's a 4. Getting minus 24.3 kilocalories per mole. Now, this means that's the reaction if, when I add this up, I get this reaction. So what have we got over here? Well, we got an H2. We got a plus a Br2. And we got plus 2H dot. And plus 2 Br dots. And that all goes to 2H dot plus 2 Br dot plus 2 HBr. So we've got all this added up here, over here, and all this down here. Now what's interesting is, just like an equation, if you have the same value on each side, they can cancel. Okay, so this cancels with that. 2H dots, 2 Br dots cancel. And you're left with H2 plus Br2. This reaction matches that reaction, so you know you haven't made a mistake. And so this is the delta H for the reaction. And what does it tell you? If delta H is negative, it tells you have an exothermic reaction. An exothermic reaction is one that releases energy. Okay? On the other hand, if it were positive, the reaction would be endothermic. All right. Let's try another problem here with bond dissociation energy. And let's just try a calculation on the monochlorination of an organic molecule. We're going to take chlorine and we're going to react it with the molecule ethene. And we're going to produce CH2 double bonded CHCl plus HCl. So here's my overall reaction. And I want you to calculate the delta H, right, the heat of reaction for this reaction. All right, what's happening here? Well, in this case, we are breaking a Cl2 and here a carbon H, right? We're breaking, let me just draw it a little differently. One of these H bonds, okay, so I'll just have a CH bonded to an H. We're breaking this bond. So I would have to go to my table and look up the bond dissociation energy for that bond. So we're breaking a Cl2, we're breaking this organic molecule CH bond, we're attaching a Cl to an organic molecule, and then we're attaching a Cl to the H. We'll draw the half reactions for these, draw the individual steps through a free radical process. Well, Cl2 can go to 2 Cl dots. That is the Cl-Cl bond breaks, and we get 2 Cl dots. And again, we'll put delta H in kilocalories per mole. Okay, so what is the delta H value for this step? Well, 2Cls has a delta H bond dissociation energy of 58. Is our value positive or negative? Is the bond forming? Bond forming is negative. This is bond breaking, so it is positive. And in the case of the organic molecule, we're breaking the bond. So we keep a CH and we have a dot there plus H dot. So again, we've broken a bond. If I go to my table, now some tables will give you a very generic value for all hydrogen carbons, and that's okay to use. You might get 104 kilocals per mole. But in actual fact, depending on the structure of the organic, the bond dissociation energy can vary from 90 to 108 kilocals or 110. So it's much better to actually use a table that actually gives you different bond dissociation energies for different organic molecules, CH groups. Now, the table I'm using actually does that. But if the table you're using just gives a generic CH value, well, then you have to use that. Just to give you an idea, the value for CH4 is often given as a generic value. And the bond dissociation energy for CH4 is 104 kilocals per mole. Right? And if that's all your table gave you, you'd have to use that. And it will affect your calculation and introduce a greater error to your calculation. Now, I actually have several organic molecules listed here. And the bond dissociation energy for the alkene CH bond is 108 kilocals per mole. Now, again, are we forming the bond? Would it be negative? No, we're breaking it. So it is plus 108. Okay. From my table. All right. So what are we doing next? Well, we're assembling the chlorine onto carbon. That is, we're taking this radical, the organic radical, reacting it with the chlorine radical. So I can write that down. And the bond dissociation energy for that is 84. Are we forming the bond or breaking the bond? We're forming the bond, so there's an energy release of 84 kilocals per mole. And of course, the last molecule that's built is HCl, and that can be formed by taking Cl dot plus H dot. And that produces HCl. The bond dissociation energy for HCl is positive, because that's bond dissociation. It's 103.1, but we're forming the bond, so it's negative 103.1. Now, I can solve this, add up my values, and what I get here is negative 187.1. Over here I get positive 166. So what does that give me? That's a 1, 2. So it looks like minus 21.1 kilocals per mole. I add this up just to double check I've made no mistake. I've got the Cl2. I've got the organic molecule. Whoa. And I've got several things. I've got 2 chlorine dots. I've got the organic dot, the organic radical. Ooh, I got a lot of things on this side. I've got 2 Cl dots, and I've got an H dot. Well, I can draw my product organic over here. Running out of room. There it goes. So I have those two right here. And then I've got 2 Cl dots, the organic dot and the H dot. So I'll write those down again. What's interesting is this is identical to this. On the opposite sides of the arrow, they cancel. And so indeed, I end up with the reaction, which is a nice check that that is what I've got up here. So there we have it. Bond dissociation energies used to calculate the heat of reaction for this reaction of organic with chlorine shows a delta H of reaction of minus 21.1 kilocalories per mole. This reaction is indeed exothermic. Okay, that's all we're going to do for bond dissociation energies. It gives you a good feel on how you can use them to calculate heats of reaction, and that when you form a bond, you get energy given off, a negative delta H, negative enthalpy. And when you break a bond, it takes energy, and you must put in the same amount of energy that you get out from forming the bond, and it's positive. And you add up bond dissociation energies to calculate heats of reaction. Now, what we want to do is look a little more closely as to the consequences of electronegativity on molecules, Lewis structures, and spend some time talking about the reality of not having what we assume informal charge. Equal sharing of electrons does not really exist. If I have identical atoms bonded to each other, this is not a Lewis structure. Why is this not a Lewis structure? Because I'm not showing the lone pairs. But if I put in the lone pairs, I've now drawn the Lewis structure. So here's the Lewis structure for Cl2. In this case, the assumptions of formal charge apply, because who's more electronegative, chlorine or chlorine? Well, it's the same molecule, so in actual fact they are of the same electronegativity, so there would be equal sharing. And there would be, the electrons should exist roughly halfway between each other in the bond. But what happens if we have different atoms bonded to each other? I'm going to just show the bond and not draw molecules, because I want to focus on the bond, such as we have here. Organic molecules could have carbon-chlorine bonds, carbon-oxygen bonds, or carbon-fluorine bonds. It turns out that chlorine is more electronegative than carbon, oxygen is more electronegative than carbon, fluorine is more electronegative than carbon. That means these atoms on the right are pulling the electrons more closely to their nuclei. Now, if you pull electrons closer to yourself, you start building up slight amount of negative charge. Not a full negative -1 charge, but you get a partial negative. Likewise, the carbon, because the electrons are pulled slightly away from it, start building up a slight positive charge. How are we going to indicate this if we wish to show it in a reaction or as a drawing? We use the Greek symbol delta to mean positive, or actually, sorry, delta to mean slight. So if I want to show a slight positive charge, or you might prefer partial as opposed to slight. Partial positive charge, I draw a delta over the chlorine and I put delta. I put a negative for the chlorine because it's drawing the electrons towards the chlorine, and the carbon a plus because it's losing electrons. Chlorine's more electronegative. And this pattern would exist over all of the atoms of the bond. Now this leads to the bond becoming what we call a polar covalent bond. It's still covalent, it's not ionic. We haven't completely transferred electrons. We haven't made full minus, full negative charges. We're just saying the electrons are slightly tilted to one atom. And this polarizes the bond. And this polarization leads to what are called bond dipoles. Bond dipoles. Now, if you look in the handout notes on page 16, and I'll just turn them myself. We can define a term called dipole moment. What is a dipole moment? Well, I can take any of these bonds and I can draw an arrow from the partial positive to the partial negative. And I often draw a little line on top of the arrow at the positive end to show the direction of a dipole. The strength of any dipole, okay, or the quantitative value of any dipole, and I'm going to give the symbol of the dipole as the Greek letter mu. That's mu. Okay, will equal the charge the amount of charge or separation of charge that has occurred multiplied by the distance of separation. All right. Now, if we apply this calculation, and let's just clear the screen, to a hypothetical situation, we can say, well, what would the dipole be in complete electron transfer? We get an ionic bond. We take one electron and we move it a distance of 1 angstrom. There's my angstrom. What would a dipole or the dipole strength be in that case? Well, if I apply my calculation, the calculation said mu equals the amount of charge separated. It's 1 electron. What's the charge on an electron? Well, 4.8 times 10 to the minus 10 electron standard units. We're moving at a distance of 1 angstrom. And 1 angstrom is 10 to the minus 8 centimeters. If I solve this, I get 4.8 times 10 to the minus 18 electron standard unit centimeters. The Debye unit, a Debye, would be equal to 1 times 10 to the minus 18 electron standard unit centimeters. So that made this 4.8 Debye. It was given the symbol D. Now think about what we just calculated here. 4.8 Debye is the polarity you get if you transfer 1 electron 1 angstrom. Now if 1 angstrom is the approximate bond length, then 4.8 Debye is the Debye you must have to become an ion. A carbon OH bond has a typical mu value. Boy, that's hard to draw with this pen. Mu equal to 1.5 Debye. Now, what's really cool is once I know this value, and I know the value that it would have if it was ionic, I can calculate a percentage covalency. Like, how far is this? What percentage is this from being ionic? Okay, well, I can take the 1.5, divide it by 4.8, divided by 4.8 times 100% equals 31.25%. Now, in this case, this tells you that your bond is only 31% ionic. I mean, it's more covalent in nature than ionic. This percentage is a very gross approximation because the bond length is quite likely not 1 angstrom. But it's close. It gives you a rough idea of what you can do with these dipole moments. And that's all we're going to do with the quantitative value of the dipole moment. From a qualitative perspective, of what use are dipole moments? Why are we interested in dipole moments? Well, it turns out, if we look at another example, a molecule, say carbon dioxide. Here's the Lewis structure for carbon dioxide, CO2 gas. Now, if I look at CO2 gas, I know oxygen's more electronegative than carbon. So carbon gets a partial positive, so here's its delta plus. Oxygen gets a delta minus. Oxygen gets a delta minus. And I can draw my dipoles towards the negative. So they're my two dipoles. Now, as we've seen, dipole moments can be measured. So CO2 could have its dipole measured. The whole molecule's dipole. Now, dipoles add together as vectors. Right? Now, I don't know how you are with vector addition, but suffice to say, this carbon-oxygen has a double bond. This carbon-oxygen has a double bond. They're both going to have the same bond lengths. Okay, so the distance of separation is the same. This is electronegative oxygen, that's electronegative oxygen. The delta minus delta pluses will be the same. The net result is this dipole and that dipole are identical. Big deal. Well, suppose you didn't know the structure of CO2. Suppose you didn't know if it was a linear structure or a bent structure. Measuring the dipole of the molecule should tell you whether the structure is bent. Think about it. This guy would have a vector this way. This guy would have the same vector that way. And when you do vector addition, if you have one that way, you can take this guy and add him down there, the same length. And the net, when you add them, would give you a vector this way. In other words, this guy would give a vector down. This guy would have a molecular dipole moment. Because the vectors are equal and opposite, it's like a tug of war. Yes, this bond has a dipole. Yes, this bond has a dipole. But once you add them up, they cancel out. If the molecule is linear, mu, in this case, would equal 0. It's experimental evidence as to the shape of a molecule. This represents just one important use for dipole moments. So dipole moments, or the mu value, depends on bond polarity and the shape of the molecule. If the molecule was bent, it would have a mu value. Mu would be something. It would have a mu value. If the molecule is linear, in this case, mu is 0 because they cancel out. Okay. The last topic we want to spend some time talking about, if we can, comes from our Lewis structures, and that is the type of formulas one can draw. Having established how to prepare Lewis formulas, assign formal charge, it's useful to know what kind of formula we're actually looking at. So let's begin with the simplest formula, and that is the empirical formula. And for all of our formulas, let's start with this molecule. You've probably seen it drawn in books like this in high school. It's called benzene. We're going to use benzene. Now, the empirical formula is the simplest, smallest whole number ratio of the atoms present in the compound. I can't use fractions, and so I have to take all of the atoms, and it turns out benzene has a hydrogen off each position, and there's carbon. How many carbons are there? 1, 2, 3, 4, 5, 6. So benzene has 6 carbons. And then off of each carbon there's 1 hydrogen, so it has 6. How many carbons to hydrogen are there? Well, there's 6 to 6. What is the smallest whole number ratio? 6 to 6 is the same as a ratio of 1 to 1. In other words, the empirical formula is C1H1. It's the smallest whole number ratio. It can be used to give us the percentage of hydrogen to carbon in the molecule. Now, the molecular formula is the true formula. The number of atoms, each type, written here. And this is what we give when we usually give a question. And the true formula can is often expressed as elemental. Sometimes the molecular formula and empirical formula match each other if you can't reduce the ratio and retain whole numbers. The structural formula comes in 2 versions. We got the first version is the valence bond formula. Valence bond formula, we'll call that A. The valence bond formula shows the covalent bonds represented by a line. So in the case of benzene, it doesn't matter where the double bonds were, you may have rotated them, it's still benzene. Notice our valence bond formula will be a Lewis structure as long as you show all the lone pairs. So this is also the Lewis structure in this case, because there are no lone pairs. If we chose to leave out the lone pairs in a valence bond formula, then it's not a Lewis structure. Now, the B part is called the condensed structural formula. Suppose I wanted to do the valence bond formula for ethane. This is C2H6. One condensed structural formula for this might be CH3 bonded to CH3. So a condensed structural formula, okay, would look like that. So if we're drawing a condensed structural formula, we're using a short form to represent the hydrogen bonds. Empirical formulas, molecular formulas, and the two types of structural formulas are very common to organic chemistry. But you notice that doesn't quite fit this formula I've drawn for benzene. What's going on there? There's a shorthand notation, if you like, which is referred to as the Polygon formula. Now, if there is no polygon, it's sometimes, and it's just lines, it's sometimes called a line formula. So the Polygon or line formula. When you draw a polygon or line formula, hydrogens are bound to carbon are determined by valency. And I'll explain that in a moment. Each vertex in a polygon, or each end of a line, is a carbon, understood to be a carbon atom. So if I drew this, it is understood that each vertex is a carbon. It is also understood there is one hydrogen off of each carbon. How? Well, we know carbon's tetravalent. We know that carbon has 4 valence electrons and needs to make 4 bonds. If I pick a carbon, say this guy, okay, look at this carbon. He has 1, 2, 3 bonds. He's missing a bond. Well, that bond he's missing, if nothing's shown, is a hydrogen. It's understood there's a hydrogen here. All right? So if you do that for every one, you see they all have 3 bonds. You might say, for benzene, why did I draw the circle? Well, we'll explain that later. To understand this symbol, we'll have to take a look at the concept of resonance. So we're not quite there yet. Let's look at some other polygon formulas. For example, what if I draw something like this? What does that mean? The end of each line is a carbon. Every one of these dots, each vertex in the line, and each end of the line is a carbon. Because this carbon has 2 bonds, I know there's 2 H's here. Since this carbon only has 1 bond, there must be 3 H's off of him. CH2, 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 CH3. Suppose I gave you the following condensed structural formula. And I said, draw a line formula for this molecule. What do? Well, for each carbon, I draw a line. So this is a carbon. That is a carbon. Well, that's that bond. Now I can draw a line up and down to the other carbon. I could draw a line to this carbon. What about to the SH? I can draw a line. And notice I bend the line just so I know there's a carbon here, right? I know there's a carbon at this intersection. If I left it like this, this would be a carbon.
So clearly, in line formulas, you must put what are called heteroatoms. Heteroatoms are any other atom other than carbon. And then you also add any H's off the heteroatom. So there you go. Now you could draw it this way, or you could draw it this way. Or you could draw it this way. Okay, so this is SH. This is all the same thing. Shape at this point is not important. We've covered a lot of different topics looking at concepts such as the definition of bond distance, atomic radius, electronegativity, bond energies, dipole moment, and different types of chemical formula.